length of the chopstick, which shortens all the time. Or in other words, there is no length scale in the chopsticks. It's a scale-free. Do you see what I mean? It's a scale-free because in this case, it's only part of the bamboo chopstick got bended. And you ask physically, why is that? Oh, because once the fiber rupture, this part is thicker, but this part is thinner because only this part remains. 变得比较薄，比较薄当然比较好弯啊，所以接下去压的时候，薄的地方就先弯，啊，旁边比较粗的就不弯，所以它就不弯了，所以就等于等效的筷子就越来越短，越来越短。So the sort of effective length got shortened progressively. Okay, and theoretically that's crucial because when a system, the length scale vanishes, just like when you crumble a piece of paper or a piece of newspaper. So that's about 20 centimeters, and that's about 15 centimeters, and that's about 10 centimeters. So in this case, there's also no length scale. It's scale-free. Okay, so we have a theory that when the system lacks a characteristic scale, length scale, it would mostly give you a power law. Okay, and in this case, very different from universality class. Of course, it has nothing to do with fractal. So this is a very different from previous story. And you probably will ask, why this is not fractal? So you need to check Wikipedia. This is periodic. Periodic is very different from self-affinity. Okay? For periodic structure, that's 2D. You need to do self-affinity to get fractal dimension, so it's different. So this is not a fractal. Okay? So the mean referee says it's a fractal, so it's a simple, it's expected. But we said this is not a fractal. Okay? It's periodic, not self-affin. Okay? So this is not fractal. Okay? So in our case, we said we managed to derive the model without invoking phase transition or SOC or fractal. So that's another setting point. Okay, right? Okay, right. So that's so this is a very important picture. The bamboo chopstick is scale-free. Okay, the length is shortened all the time. And here comes. So these three are chopstick, and these three are from spaghetti. Okay, and I'll explain why is that. So so that is energy. So that's a small energy, small noise, loud noise, medium noise. How many times it happens? So it's called GR law. And crumpling paper has that. But these two are unique to chopstick and spaghetti. In this case, the x-axis is how long you have waited after the main shock. So for earthquake, it's easy to explain. When you have a main earthquake, you wait 1 day, you probably get a big aftershock. But if you wait 1 week, the aftershock will be even smaller. Okay, so in the second law, you measure the frequency. Let's say every 24 hours, how many aftershock you get. It turned out to decrease with the time from the main shock. Okay, and that's reasonable because otherwise that would be the end of the world. Always the frequency of the Earth's aftershock get less frequent. Okay, but turn out that if you put this is how many days after the main earthquake, and this is the frequency of the aftershock, it turned out to be also a power law, and it's called a Maury law, and it's empirical. Okay, and no one knows why. It's an empirical law. Okay, and this is called Bass law, and Bass law says if you have a large main shock, then the aftershock, the bigger the aftershock, will be bigger. Of course, if the aftershock is bigger than the main shock, then this one will be the main shock, this one will be the pre-shock. Okay, but what he observed is that if you take the magnitude of the main shock and the largest aftershock and take the ratio, it turns out to be a constant. That means this ratio is the same as the small main shock and his biggest aftershock. The ratio is the same. Okay, it's called the Bass law. So these three are the three most important empirical law in earthquake. It turned out that chopsticks And spaghetti also have that. Okay, so we think it's kind of cool. Okay. Question. Right. So let me okay, so that's Omori. Okay. So you can see Omori. So he's trying to predict that San Francisco is safe, but later he got a big earthquake. So that's a joke. Okay. Anyway, so that's Omori, and that's a bass. Okay. And okay, I will forget about that. So there's a different all sort of theory. Okay. So our theory is very different from other people. So right. Okay. Come to conclusion. Okay. There's no conclusion. Okay. So I'll just tell you what sort of other things after spaghetti, after chopstick, what other things we also our students. So our students are mostly undergraduate. Okay. So don't expect too sophisticated. So zip law. Remember the Shakespeare, the Romeo and Juliet. Okay. So there is a Nature paper. Okay, which found that if you take a music note, 就是拿钢琴曲，可以吗？ If you try to do a zip law, so how do you do that? For instance, it's very hard for C 大调叫什么 ？For a C major. What is C? C is a do. Is a do. 是不是 C 是 do? So you take all the do, pick up all the do. And if there are, let's say, 6 notes between neighboring do, you call it a word. Okay? And if there are 4 notes before the next and next note, you call it a different word. So you can do a similar analysis. And he found that for music note, it also obeys zip law. And it went on to appear in Nature. Okay, so we try to do different things. We try to do, okay, let me see. So that's zip law. So I said zip is a linguistic in Harvard about 1920 or 30. So in those days, doing a statistic is very popular, 很夯，但现在不夯。So now in Harvard linguistics, this guy is a king, Chopstick. Okay, so now in Harvard, people don't talk about statistics; they despise it. Okay, they try a totally different approach, and that's where. So that's science. So now they don't use statistics in linguistics. Anyway, that's a story. So anyway, that's what I try to do. So this is what we try to do. We try to find the music note in beauty. How to quantitatively describe beauty. So beauty, so you have painting, you have structure, architecture, you have sculpture. So they are present to look at, especially, okay. They are present to look at. So it's just like music note. So if music note obey zip law, and do they also obey zip law? But in order to answer that, you have to quantitatively describe the statistics in painting, architecture, and sculpture. So you need to find the basic note. Okay? And because these are our typical example of beauty, 美术里面最标准的, okay? So that's something we're working on, okay? Try to find a common, so if we can find a zip law in these cases, so that would say the zip law is more universal, okay? It's not just happen on classic or music notes, but it happens on everything that's agreeable. Okay, that has a rule. Okay, of course painting has a rule, okay? Architecture has a rule, just like grammar. Okay? So it would not be surprising if they obey zip law. So that's one thing we're trying to do. And that's another thing. We try to ask why, when you tear a paper, why do you get small sound and big sound? You said that's a stupid question. Why? Because apparently, you see, this part it's sort of zigzag, okay? So that will give you a different parses of sound. But if you try to think it more closely, this seems to be a random process, okay? But turn out that the zigzag will give a power law noise, so that's not expected. And probably you say, because of fiber. But I'll tell you that we also tried on aluminum foil. For aluminum foil, there's no fiber, but also it gets a zigzag and you get a power law. So that seems it has something to do with fiber, okay? Something more fundamental. So that's one thing. And almost the end. Okay, so that's another thing. Your earphone, why is also entangled? Okay, so apparently a lot of people have asked that. Okay, so that has been explained by a PNAS paper. Okay, so we try to also work on it, but instead of asking that, because that had already been answered. Okay, PNAS. Okay, and also UCSD. 哎，你认得这个人吗 ？UCSD. I don't know. Okay, anyway, so we try to do what? We try to link the entanglement to these three phenomena. Okay. And why is that? So I'll do another demonstration. Okay, 你不要拿到它。See, when I try to turn it, what do you expect? Tell me, before I go on. What do you expect to see? If I keep twisting it. Shorten, okay, what else? See? You start to resemble sort of helix, okay? If you use paper, that's much quicker. See? In DNA, people found that. It's called a supercoil. Okay? So what we are trying to say is, if you sort of rotate a thin, very thin, very narrow strip, it resembles a DNA. But if you do the same thing on a bigger cross section, 就像你毛巾, every morning when you wash your 毛巾叫什么? Your towel, you try to wring the water out of it. So you do this. See? Okay. It looks like a double helix, alpha helix. Okay, you get two sections of helix. Okay, so it seems that depending on the size of the cross section, you can mimic sort of a protein and DNA. That's what we believe. Okay. And right. And I think none of you are from astronomy department. In astronomy, there's something called a coronal mass ejection. That means the sun, sometimes they will eject a heavy ion with a speed almost close to the speed of light. Okay, and so the astronomy, they believe that it's due to a process called a magnetic field reconnection. And so these are magnetic field lines. So the magnetic field, when they crosses, they will entangle. When they entangle, there will be enormous amount of magnetic energy. So it's unstable. So they will sort of reconnect themselves and emit the energy. So we try to calculate what is the probability of the entanglement. So just like earphone, okay? So that's another project we're doing this. And okay, that's another thing. We try to study when you puncture a surface. So 有几个花瓣, how many sort of leaves? Is there a sort of regularity? And that is something probably I can show you. See? So that's smooth one. There'll be wrinkles, okay? When you try to distort a surface, there will inevitably a wrinkle. It's called a D-cone, ABCD, D-cone, okay? So you can see D-cone is just like a center point. There are maximum and low and minimum, okay? So we try to ask, does the eventual rupture, does this line are determined by the D-cone before it breaks? Okay, and you say, it's reasonable, but we try to ask if the paper gets thicker. Let's say if it's like a piece of wood, when you put a nail on a wood, when you penetrate, you also get this. And we believe that even for a very thick thing, all these things are determined by two-dimensional property. We believe it's something to do with the surface distortion. Okay, so as you can see, it's a sort of embarrassment. We've been working on rupture, puncture. So all these are not taught in standard solid-state class. In solid class, we are studying crystal. Okay, nice things, but these things are very different. They are sort of study how material behave when they fail. So English is called a material failure. So when colleagues ask, what are you interested? What are you interested in? You say, I'm currently working on failure. Okay, so it's embarrassment. Okay, so that's that. Okay, so these are material failure, and so that's another thing, and that's another thing. Rattle sounds. So probably some of you know, but this is a junior student working on it. Probably you already know that. That's called rattle sound. Okay, so if your washing machine is very old, you'll hear that every day. That's called rattle sound. Okay, so we need to know why, because the washing machine company, they're very interested in it, because that is the headache. Okay, most of the customer complaints are from that. Okay, what causes that, and is there any physics you can say about it? For instance, the frequency. Okay, so that's a rattle sound. And that's the heartbeat. So heartbeat, people believe that heartbeat. So for heartbeat, they are roughly regular, but they are not really regular. So there is a deviation, and people believe that it's like a power law. Where is it? See, power law with the exponent. So people use that power law to detect. It's really doctor. It's a disease. Okay, people believe that when you're healthy, your heartbeat has a typical exponent of -1. But if you contract this disease, when the medical analysis, before they can detect it, if you measure your heartbeat, you will deviate drastically from -1. So they use the power law to detect patients before they actually know it, contract the disease. So it's been used. But when you use the statistics, we found it's not a power law. It's not a power law. So that means this method is seriously wrong. You use that to predict. Okay, so one student is using that, and these diseases are propagated by a drug. Okay, with a very romantic name. It's called a kissing bug. Okay, you can check. Okay, so it's a disease. So heartbeat, and that's the neural activity of the brain. Okay, so see, brain functional network. They also call it's a power law. It's a PRL, and using our method, it is not a power law. So that means after we have the method for the statistics, there are a lot of things that we can do. Okay, because people say it's power law. Now we know it's not, according to statistics. Then the next question is, do you have a patient? Do you have a time to answer what new physics people have missed, or what new medical information people have missed? So there are a lot of things we can do. Okay. So we need people to collaborate, because these things are all too advanced for undergraduates. But we're trying to do that. See, brain activity is scale free. So a lot of people are using that, medical doctor using power law or different stuff. Right. Okay, forget about that. That's me so soon. But, okay. Anyway, so that's that. Okay. All right. Thanks for your attention. Yeah.
Okay. Thank you for this interesting talk. Any questions or comments?
So I want to ask about log mode the plus. Yeah, and you said that the y-axis is the number of the noise, right?
Now, you can be anything, but for most cases when we study, y is the probability, means how many times it happens. For instance, if this is earthquake, so that's 无感地震, that's small earthquake. So Y will be how many times you detect the small earthquake, let's say in a day or in a week. So the number of times, so it's proportional to probability. But there are other cases, for instance, in physics, you can measure the pressure versus volume of an ideal gas, right? So it can be anything. So the point is, when you do an experiment, you get data point, but you need to fit it with the function. For most people just, for instance, for power law, people just say, it looks straight, and then they will measure the deviation. If the deviation is smaller than alpha, they say it's good. Okay, but so the message is, this is not good enough. Okay, this is not good enough. You get fooled from time to time. Okay, just like the 8 very famous example, power example, we proved that they're all wrong. But don't ask me why they're wrong, because we do not know the physics behind it. We do not know geography, we do not know earthquake, we do not know medicine. All we know is using a statistical information theory, they are wrong. So the next question is, what new medical information or what new tectonic information you can get by studying that? Okay. See, I mean, the data point, they always have deviation. So you shouldn't trust your eye or trust your intuition. That's not good enough. You need to use a more rigorous method, and that's statistics. Okay, and we do not know statistics, but we can borrow it from the Institute of Statistics. Okay, they have a lot of weapons. We just take it and use it. Yeah, 请说。
I mean, so Professor, you claim that if you do speeding with power law, there will be a lot of loss of information, right?
You lose information. Lose means bad. So if you use, for instance, for earthquake, if you use a double power law, it's better. So that means it retains more information.
Yes.
But even that, when you have raw data and you feed it with function, there are always information loss. It's just a matter of how much you lose. A better model lose less information.
Okay, but I mean, because there's a slide, so you compare the AIC for like simple.
The smaller AIC, which means better.
Yes, but because the number of AIC, their difference is not. I mean, I think they are within 0.1%. The difference.
Very good.
But so it means that AIC is very sensitive to the difference.
No. Which?
I think it's.
I'll do that. Okay. Anyway, so when you calculate, for instance, for earthquake, okay, you take the data for, as we do, take the last 33 years, so a lot of data. You calculate AIC for single power law, so you get something like, I don't know, 100,000 something. You get a big number. When you fit it with a double power law, you also get 10,000 something. So the difference are probably, I forgot, the difference was something like 6 or 7. So you ask 6 compared with 100,000 is so tiny. So why can you trust it? So the statistical friend, they will tell us that the difference 6 is not to compare with the 100,000, but compare with another number, which is 2.8. So 6 is big enough, then 2.8, then statistically they can prove it. Don't ask me how. They can prove it. You can reject the power law. So that means the difference is not to compare with the AIC number, but compare with something that I call, I said 科大 那个小姐她知道叫 likelihood ratio test. Yeah, you need to check that likelihood ratio test, LRT. You can check Wikipedia. Yeah.
Thank you.
Yeah. Don't try to understand it because we tried, but it's very hard. So you just trust it. Okay, you just trust it and use it. Okay. So when referee attacked it, he said, "Don't ask me, ask my collaborator." And when they asked the collaborator would just give a lot of statistical jargon. I said, I'll give up.
Okay. Just a question about when you use AIC, there are other information criteria in statistics which punish the number of parameters differently.
You mean
use
AIC,
two times
AIC has two terms.
Yeah,
One term punish if you use too many parameters,
Yeah.
you punish it.
You punish it by 2k. There are other
Yeah.
information criteria which have different numbers.
Yeah, that's right. So these are sort of, they are different criteria. In here we use AIC, and they are BIC and something. And the statistical friend, they will tell you that why AIC is better. There's criteria. So you can check. So BIC is rarely used. Okay. I vaguely remember that. It says that when your fitting function is very close to the real function, God knows what, then you use BIC. But mostly you do not know what is the real function, because only God knows that. God forbid, okay? So most cases, your function, fitting function, is never close to the real function. In that case, AIC is better. So there are sort of reason why. So he's correct. In statistics, there are all kinds of criteria. But in this case, they can convince you that AIC is better than BIC or other stuff.
Better because of the deviation, or because if you use BIC, then it will be a straight up.
I don't know, don't ask me. 你问我的破功了，对吧？这样
give the same
My-
result,
that's
The same result as the straight up.
yeah.
Model.
Give us sort of the same result with a little bit.
Yeah, because in statistics they also use mostly AIC. Yeah, because it is hard to believe that you can pick one or two fitting functions that are real function. It's mostly wrong. So mostly the function you pick, the fitting function, are never real, the real one. So in that case, you shouldn't use BIC. Or in case you do not know BIC, B is Bayesian. Okay, yeah, Bayesian information criteria. So you can check Wikipedia. There are AIC and BIC, and it tells that BIC is getting more and more obsolete. Okay, AIC is more popular.
So from the AIC analysis, it suggests that.
Oh, can ask other question. I don't know a shit about AIC. Okay, I just borrowed it from my collaborator. Okay, don't attack me.
Just from the
Okay.
analysis, it says that it suggests that the single particle model may not be the best fit.
It may not be the best fit for for all these popular models.
So is it possible that the similarity of the earthquake and the breaking the chopstick is just a coincidence?
Yes or wrong? Okay. There is a Nature paper by a seismologist. He says that he believed that, according to his survey, earthquake, the reason why earthquake is probably not a power law is because there's three kinds of earthquake: converging, diverging, I forgot, the other probably sliding. And he said that he's been able to sort of distinguish all these three. And it turned out that for each mode, it's a perfect power law. But in most earthquake, it's a mixture. So that's why he suspects that the reason why the fitting is bad is because you were not able to separate different modes. If you can do that, he believed that you can get a perfect power law. 有三种，可以吗？你可以看有这种的，还有这种的，还有这种的。Okay, you can check our paper. Yeah, there's a reference on the back. Okay, and yeah, 反正我因为because when we submit to PRE, the referee tries to ask us, you said these 8 examples are not power law. Can you explain it? And we said, we only know the statistics. We do not know geology. We do not know earthquake. He says, no, you have to say something. So we bullshit something. Okay. So for instance, for brain neuron activity, we believe it's not earthquake probably because if you use this side, probably is a power law. For this side, probably a power law. So it's probably something like that. So when you measure data from these two things, so you don't get a power law probably. These two hemispheres, they do very different job. So I think it's possible. Yeah. And for Sandpire, we also found that it's not a power law, and we bullshit that for Sandpire model, it's a numerical model. When you sprinkle the sand, you get more than one sand dune. So there's interaction between different dunes. So probably that screw up the power law. So, but don't trust us. I mean, it's just.
So in your example, you say you crumple one piece, one paper.
Yeah, we do that. We also do